It's possible to use acid-base reactions in a quantitative way to do what are known as titrations. This is a way to quantify the amount of acid or base that might be present in a solution. Um, and so, in this type of process, we would have a solution of unknown concentration that we would put in, say, an Erlenmeyer flask, as shown here, and we would then add what is known as an indicator. It's a compound that changes color at a specified pH when the neutralization occurs. And we would be adding another solution of known concentration to that so that we end up doing our neutralization reaction and can then quantify the amount of solution that we have added from the burette. So once we have carefully measured the amount of solution that has been added, we can do some calculations and figure out how much of the um, moles of the species that might be present in the Erlenmeyer flask. Shown here is an example of a titration in which a solution is being added from a burette to an unknown concentration of another solution in the Erlenmeyer flask that contains also the indicator, in this case phenolphthalein. Phenolphthalein, when it is acidic, is colorless, so the adding of the base from the burette will change color to a pink color once it becomes basic. You are looking for the first faint pink color that does not disappear, so by adding some of the solution from the burette very carefully and drop by drop near the point where the pink color just starts to appear, the volume that you have delivered at this point is then measured. If you add just a little bit more, you would get a dark pink color, so you have essentially overshot the endpoint of this titration, and this would lead to some error associated with determining the concentration of the acid in the Erlenmeyer flask. So if we then measure the difference between the two volumes and know the original concentration of the solution, the base that was in the burette, as an example of a question that you might encounter involving a titration, we have 25 milliliters of a solution that contains an unknown amount of potassium hydroxide and is titrated with HCl. You see the balanced chemical reaction here, and this requires 29.20 milliliters of a 0.112 molar HCl solution to completely neutralize that solution. The question asks, what is the molar concentration of the potassium hydroxide? So in this case, we're going to start with the volume of the hydrochloric acid that's used to do the titration. We are going to first convert the milliliters to liters, and of course we do that by dividing by 1,000 milliliters for every 1 liter. We cancel the milliliters. We use the molarity of the hydrochloric acid solution to cancel the HCl, both numerator and denominator, along with the liters. This will give us the moles of HCl that was used. We then look at the balanced chemical reaction and see that the stoichiometry between potassium hydroxide and HCl is 1:1. And so if we were to solve this at this point, we would get the number of moles of potassium hydroxide, noticing that there are 3 significant digits in the molarity of the HCl. At this stage, then, to determine the molarity of the potassium hydroxide, we would need to divide the number of moles by the liters of the solution that we started with up in the first sentence of the question, making sure that we convert that to liters. And so doing the math, we find that we get 1.443 moles per liter. and then with 3 significant digits, it's 1.44 molar. Finally, we need to discuss some of the acid-base reactions that potentially can form gases. The classic example of this is the reaction of some sort of carbonate compound with an acid of some sort, such as the strong acid hydrochloric acid, as you see here. And this produces carbon dioxide gas along with the ionic compound sodium chloride dissolved in the water. There are a couple of other examples of gas forming reactions. Sulfites will also produce a gas when reacted with an acid. In this case, the gas is sulfur dioxide. The reaction is very similar to the carbonate reaction. And then finally, sulfides will also produce the gas hydrogen sulfide. This is the stink of rotten eggs that is produced. So, as an example of this in writing the complete ionic and the net ionic reaction, if we react hydrochloric acid with sodium carbonate, we can have the acid HCl react with sodium carbonate. It takes 2 HCl's to do this reaction. The product initially is 2 sodium chlorides plus carbonic acid, but the carbonic acid is not stable, and so that H2CO3 then decomposes further into then water and the carbon dioxide. So this is our molecular equation. If we then take all of the ionic species, the strong electrolytes, and break them into their component ions, so the HCl is dissociated into H plus and Cl minus. The sodium carbonate, being an ionic compound, is a strong electrolyte as well. The product, sodium chloride, is a strong electrolyte, but water and CO2 are molecular species, and they remain together. We can notice that we have spectator ions in this case. The sodium and the chloride ions can be canceled. And then when we write our net ionic reaction, we have 2 hydrogen ions plus carbonate forming a water and CO2.